In the last section, we learned about exponential graphs and what they look like. So this is what an exponential function looks like. In section 3.2, we will see what a logarithmic function looks like. And basically, it's the inverse of the exponential function. And so the graph for the log is going to look like the blue function here. So if you notice, they are inverses. So the line y equals x is the reflecting line for the two functions. So if we look at our handout, the definition for a logarithmic function is for x greater than 0, a greater than 0, and a does not equal to 1, y is equal to log ax if and only if x is equal to a raised to the power of y. The function f of x is equal to log base a of x is the logarithmic function with base e. So basically, if you have an exponential function, we can write the equivalent log function as follows. So notice that the base a is the subscript here, and then we have a over here. And this log is equal to y, and y is always going to be that exponent here. And then we have dx and dx. So something I like to always say is that the log is always equal to the exponent. And this statement helps you in writing from one form to the other. So in example 1, it says write each equation in its equivalent form. So right now it's written in log form, so we want to write it as an exponential function. So we can start with the base. The base is 7. And then I would ask myself, the log is equal to 3. So the log is always equal to the exponent. So in this case, since it's equal to 3, that makes 3 the exponent. So this would be the equivalent exponential function. If we look at letter B, the base is b. The log is equal to 2, so that's going to be your exponent, 25. We don't have to solve for these as we're just writing the equivalent form. So the base here is 4. The log is equal to y, so y is your exponent, 26. If we look at example 2, these are written in exponential form. Now we want to write it in logarithmic form. So we're going to write the word log. And then the base is 2. And the log is always equal to the exponent. So 5 is your exponent. And then we have x. So here my base is b. The log is equal to the exponent, so 3 would be what it's equal to. And then we have 27. And then here we have log. My base is e. The log is equal to the exponent. My exponent is y. 33. So log e is a special logarithm. And so anytime we see log e, this is going to be a natural logarithm, which we'll talk about in a few minutes. So from now on, if you see log e, we can write it as ln 33 is equal to y. So log e is going to be replaced by ln. And we'll get into more details in a little bit. So what we want to do is evaluate these functions. And so log 10 of 100, we want to know what is that equal to. So let's call this x. So the way the log works is basically you want to ask yourself, what power does the 10 have to be to give me 100? So the power has to be 2 because 10 squared is 100. Or we can use the one-to-one property that we learned in the last section. So first we can change this to an exponential form. So this would be 10 raised to the power of x of 100. And I can rewrite this as, instead of 100, I can write it as 10 squared. And since the bases are the same, I can set the exponents equal to each other. So log 10 of 100 is equal to 2. So if we look at letter B, what power does 5 have to be to give us 25? 5 would have to be 2. 5 squared would be 25. However, let's work it out. So we can change this to exponential form. And then we can write 25 as 5 squared. So log 525 is 2. Okay, so same here. Log 36 of 6. So my base is 36. The log is equal to x, so that's my power. And then we have 6. So here we can do the same thing, is try to write it so the bases are the same. So 36 is the same as 6 squared. So this would be 6 2x is equal to 6. Set the exponents equal to each other. 2x is equal to 1. Solve for x. So x is a half. Divide by 2 on both sides. And the next one we have 3 to the x is equal to the 7th root of 3. Since we have a root here, the 7th root, we can rewrite it as 3 to the 1/7. Remember the roots, we can write it as exponents, as fractions, with the index here being your denominator in the fraction. So now we can see that x is going to be 1/7. Letter E, we have log 5 of 1 divided by 125, set it equal to x. So this would be 5 to the x is equal to 1 over 125. So I can try to make them to have the same base. 125 is the same as 5 cubed. But notice that we have 1 divided by 5 cubed. So we can use the exponent rules, and if we divide this, this would be 5 raised to the negative 3. And so we get x equals negative 3. Okay, let's try letter F. F through I are special cases, and you'll see why here in a second. So we have log 9 is equal to x. So here x is going to be equal to 1. So 9 to the first power is 1. So if I give you another example that's similar to this one, let's say we have log of 50 of 50. Okay, so it looks very similar to this one, except instead of 9 we have 50. Notice what happens. 50 to the x power is equal to 50. So x is still going to be 1. Well, what if we had log of 1000 of 1000 is equal to x? So we would have 1000 is equal to 1000 is equal to x. So if you notice, as long as these two numbers are the same, our answer is always equal to 1. Okay, so that's actually a property on the next page. That's going to be property number 2. If the base and the number are exactly the same, then your log is always going to be equal to 1. Let's look at letter H or letter G. So we have log 8 of 1 is equal to some number. I have 8x is equal to 1. So any power, if x is 1, that would be too big because that would give us 8. So it has to be less than 1. But what number would always give us a 1 if it's an exponent? And so this is actually a rule. So in this case, x has to be 0. A to the 0 power is equal to 1. And so if I give you some more examples, log 10 of 1, then x has to be 0. Okay, or I can say log of 100,000. So it doesn't matter. This is going to be 0. So if you have a 1 here, then your answer will always be x equals 0. So that leads us to the first property on the next page. Log base a of 1 is always going to be equal to 0. And then on the next one we have log 778 is equal to some number, x. So if I change this to exponential, my base is 7. So here you can see the bases are the same. So x is going to be equal to 8. Okay. So notice that the base and this number, which is then raised to another number, are the same, 7, 7. So if we had something like log 50 of 50, 15, then this is just going to be 15. Okay. So notice that 50s are the same, so your answer is just going to be that exponent. So you can see here your answer is an exponent. So that's part of this row here, number 3. If you have the same base, and this is the base of an exponential expression, then your answer is just going to be that exponent x. And then the last one here, this is actually written as an exponent because notice we start with the 3 instead of log. So I'm going to change this to a log. My base is 3. The log is always equal to the exponent. In this case, my exponent is log 3 of 17. So in order for these to be equivalent or equal to each other, then x has to be 17. So in this case, if we have base 3 raised to a log with the same base, then your answer is going to be this number here, 17. And that's going to be. Okay, so if you notice, we have the base is square root of 7, then we have the square root of 7. So that's going to be property number 2. They're the same, so that's equal to 1. Okay, so here the square root of 7. Log square root of 7 of square root of 7 is equal to 1. If you want, you can work it out. So we can set it equal to x and change it to exponential function to give us the x equals 1. Letter C. For letter C, we have 6 raised to the power of log 6, 20. And so this is the property number 3, which is here. And so my answer here would just be 20. We can work it out by setting it to exponential function. So we would get x is equal to 20. On letter D, we have log base 3 of x equals to log base 3 of 12. So in this example, we can see that the base is the same, so we can set x equal to 12. In letter E, again, the base is the same, so we're using property number 4, the one-to-one property. So we can take x squared plus 3 and set it equal to 12. Solve for x by subtracting 3. So we get x squared is equal to 9. Take the square root on both sides. So we get plus or minus 3. In logarithms, we have to make sure that this is a solution. And so anything that we get in here should be positive. So we plug in the 3. 3 squared equals 9 plus 3 is 12. And negative 3 squared plus 3 is equal to 12 as well. So later we'll talk about the domain and why it's important that these are positive results. So for the next part, I'm going to use decimals to graph these functions. So let me just, so the first one is f of x equals to the exponential function of 2 to the x. So on our handout, that's f of x. So that's just an exponential function. And then g of x is the log. So the log here is in black, and you can see they're 1 to 1. So I'm going to get rid of this exponential one. And then for h of x, it says negative 1 plus log 2 of x. So if I pick a point, let's say this point here, 1, 0. If we have negative 1, if we're adding a negative 1, let's see what happens to the graph. So if you notice the graph shifted down. And so that's using the same transformations as we had before. So in section 1.7. So if we're adding or subtracting a number on the outside of the log, then the graph moves up or down. Notice if it was a positive one, then the graph would move up. Okay, so now let's look at what happens if we add a number inside of the log part. So here we're adding a plus 3. So the graph is going to shift 3 units to the left. So the transformations work the same way as they did in 1.7. So this negative 1 tells us to shift down, and this plus 3 tells me to shift left. Okay, so let's go on to the next page. So the domain of a logarithmic function of the form f of x equals log bx is a set of all positive real numbers. And these are just some examples of some logarithmic functions. So if we want to find the domain, you want to set the parentheses greater than 0. If I add a 5, then we get x is greater than 5. So your domain will be from 5 to infinity. We want it to be greater than 0 because you can see the graph here is going to get closer and closer to 0, but it's never going to get to it. And then for b, we have the natural log, which is the same as log base e. We still set the inside parentheses equal to greater than 0. So at 2, x is greater than 2, so my domain will be from 2 to infinity. And the next example, we have 2 minus x greater than 0. Subtract 2. So I divide by negative 1. Since I'm dividing by a negative number, This is going to switch the sign to less than. So my domain here is going to be anything less than 2. So that's going to be negative infinity to positive 2. And you can see here, as long as the inside is positive, then we can take the natural logarithm. And so on the next one, we have x squared is greater than 0. So x squared is, x is greater than 0. However, notice here that if you put a negative number here, let's say we had negative 2, then this will become a positive 4, and that's still going to be okay. So your domain is actually from negative infinity to 0, and from 0 to infinity. So in this case, it's all real numbers except for 0, because whatever we put in for x, it's always going to make this a positive number. So this was section 3.2.